Jane, thank
Sure.
you for the introduction. Good morning, good afternoon, everyone. Uh, so the topic is pretty much being clear, right? We will be talking about AI-driven techniques for noise filtration in the software validation logs. Uh, so this is the outline, right? We'll be talking about topic in bit of detail, right? I'll give some more context. What is the background, right, from where this topic is coming in? Some high-level challenges, problem statement, solution, machine learning flow, learnings and takeaways. But just to set some more initial context, what we have seen in the last 1 decade is that software and hardware, they have played exceptionally, I would say, a pivotal role in the machine learning, deep learning, and AI space, right? All the advancement in the software and hardware helps in these areas. But the important aspect is that while software and hardware have played an important role in AI and ML, the corresponding or the reverse is also true, which means that there is a huge opportunity to apply the AI and ML in the software and the hardware operations. And this is where this complete presentation is all about. We just want to give the understanding that while we have a highly competent software and hardware engineering teams, they have a very niche, I would say, skill set where they create I would say, a very competitive softwares and so on. They always have different kind of operational challenges in their software processes or their software delivery processes. While they have a very good understanding on their domain, sometimes they don't probably understand that the usage of AI and ML can help them to be more efficient and effective, right? They can apply different techniques, be it coming from machine learning, deep learning, or the AI learnings, right, in their operational processes and try to solve their problems and make it more effective with the usage of the data and the corresponding AI and ML technique. And that's where this paper comes into picture, right? So we'll be talking about a small case study where we demonstrate that how AI/ML can help us to solve some of the operational challenges in the software delivery process. Now, just to kind of extend the introduction here, this paper or this presentation basically explores the integration of the software testing of the log files, uh, diagnostic. I'll also explain what exactly is software testing log files diagnostic with the integration of the NLP, which is, I would say, pretty much a buzz in the last 1 decade and got a lot of attention because of Gen AI in the last couple of years, and some of the machine learning and the deep learning techniques. Now, what exactly is happening is we try to combine the NLP for interpreting the data with the help of some of the machine learning techniques like ensemble or the deep learning techniques, which improved the error and the query classifications of the test logs. Now, what is the benefit is that this method of introducing the machine learning and AI, it does not just reduce the manual interventions where some humans are trying to do the classifications of the logs, but they also sets new standard of having automated precise systems of the diagnostics. So essentially what we are talking is we are talking about the integration of the software in testing collaterals with the machine learning collateral side. So it's like a marriage of the software development processes with the machine learning processes, right? That's the crux of the story. Now, just to give some more background, okay, what is this process? What exactly we are talking about? So the software development process is I would say, it's an end-to-end product life cycle where it starts with requirement phase and it goes down to the delivery phase or the post-delivery maintenance phase, and it has different phases in between. For example, requirement design, then you have implementation, testing, and so on. So what we are talking about is a small part of the software development process, which is called the bug triaging. Now, what is bug triaging is that whenever we test any software, right, that software basically, when tested, it provides certain logs, right? It is called the test logs. Now, these test logs are being analyzed by the some of the test engineers or the triage engineers, and they get into these test logs, try to read those test logs and figure it out whether there are certain issues which is being detected as a part of the execution by reading through these logs. And eventually, if they find some issues, they raise a bug to a development team, right? And that's the process. Now, essentially what is happening is that this process is called the bug error triage flow. Okay, at a high level, what is happening here is, if I just want to quickly share, is one, that software development projects are being validated for thousands of use cases by various soft system integration and the validation techniques. What it means is that there are different kind of testings which are happening, right? Functional testing, performance testing on different level of testing, be it the integration testing or the performance testing or some other milestone based testing. But what essentially we are doing is we are validating thousands of use cases uh, by the systems and the system integration and the validation technique. Now, obviously, each of these tests executed as a part of the validation cycle, which generates the validation logs. Now, these validation logs are of different types and different sizes, right? Some could be just maybe 10 KB or 10 lines of code. Some could be like thousands of lines of code and so on. Depends upon the execution use case, the test case, environment, and many other factors. And generally, the test types are the basic acceptance tests, sanity tests, stability tests, functional tests, integration tests, and many, right? So you always have different kind of test levels and different kind of test cases. And eventually what is happening is you are infeeding your software build into these different test levels, and they are generating different kind of test logs. Okay, so this is what.
Quick question. What is tape in under test type?
Tape in is basically when you are into let's say a semiconductor kind of environment. Okay, there are two different life cycles which goes in. One is called the hardware life cycle, where you're generating, let's say, the hardware or the chip, right, SoCs. And then of course you have the software life cycle. The software is like firmware and driver, and that's firmware and driver basically follows the software development cycle, and that eventually get, let's say, integrated on the hardware. So tape-in is, you can probably consider at a very high level, is where you are trying to bring the hardware with the software as an integration. Right, that's the most simplest way of understanding this. Right,
Thank
so
you.
you are bringing that. So it's like not just testing the software part, but also bringing the hardware flavor also into it.
Okay, wow,
Okay.
it's complex. So thank you.
Yeah. So essentially, what is happening, as I explained, right, software release builds are fed into a test environment. Testing generate logs for each and every executions, right, for all these different kind of logs and different kind of tests and everything. Then we have a test engineer or a triage engineer which manually analyze these logs. They may probably use some scripts or something, or they would do manually, but again, uh, they try to analyze the logs and then read through each and every logs and then figure it out whether there is any error or not, right? And each part of the log is being categorized whether there is a noise or whether there is a real error, right? If there are real error, then we need to pass that information, and then we need to triage it to the team by raising a bug, right? That's generally the bug triage flow. Now, what are the challenges, right? The challenge is that this is the files are of different nature, right? So you may have test files, which are .log files. You have .csv file. You may have .error file, and many other files, right? Now, each log file has varied format, right? As I said, .log file is one format, and even the different test type and the test level may have different format. For example, if you're testing on some specific test scenarios in integration versus functional versus maybe uh, let's say performance and XYZ, right? Every test based on its nature, based on its environment, have a different format also, right? So, and then you are running these test cycles manually or semi-automated or automated thousands and thousands of times on daily and weekly basis, which means you are generating a high volume of logs in a specific period of time, right? So what exactly this means is that this uh, exemplifies the big data 3V problem. Now, what is big data 3V problem is that you are talking about the volume of the data here, you're talking about the velocity of the data here, and you're talking about the veracity or the variety of data. When we say volume of data, which means that there is a huge amount of logs which are generated for each and every test execution, and there are many, as I said, thousands of executions happening every day on different setups and environments, right? So you have huge amount of logs which are getting generated. Velocity, why this is a velocity problem is because of the involvement of various tests working in parallel across different test cases, different softwares and ingredients, right? You are generating the logs on a very, I would say, frequent basis, right? So let's say every hour you are probably generating thousands of logs. And then there is a use case of variety of the logs. When I'm saying variety, you have different types of file formats, for example, .log, .csv. They could be formats which are sometimes structured, sometimes semi-structured, sometimes unstructured, depend upon the test case, depend upon the environment, how it is being written, how it's being executed. So it's a very, I would say, a typical problem of volume, velocity, and variety or veracity, right? Whatever you want to call it. But it's a big data 3V problem, which can also be classified here. Now, what is our problem statement? What is the problem statement we try to solve with our validation team, right, under the software development product life cycle? The validation team, it is, as I said, it's facing the 3V challenges, right? So this 3V challenges is the volume, velocity, and the variety, right? Which makes it identification of errors a very labor intensive and error prone activity. So when I'm saying labor intensive means even if you try to write a script, you cannot rely on that script. That one script will solve the purpose, right? Because the scripts will have to be adjusted, they have to be written, they have to be managed, they have to be changed for different formats and different types. And you will always have the error proneness because someone is going to write those scripts, someone is going to read the output of those scripts and so on, right? So script can only help you to some extent, but it still come up with some kind of labor intensiveness and error prone, which eventually impacts the turnaround time, right, of the let's say the complete diagnostic and the triage process. So obviously, since the current method is pretty much manual or semi-automated with uses of certain regex operation, it's being a very time-consuming, maintenance-heavy, and prone to human oversight activities. And generally, on an average, it takes like a couple of hours, right, to triage the logs because you have to go to those big logs and understand what exactly is happening. And that's where the solution comes into picture. So the solution is that how our validation engineers, right, as a part of their operational process, can leverage the possibilities of machine learnings or AI to do some of these tasks, right, using that kind of intelligence and try to minimize, let's say, the usage of the human intervention and let's say some ad hoc scripting. So what is being done here is that there is a machine learning or deep learning solution which is being created to predict the errors from these logs and filter the noise, right? So obviously any log will have errors information and the noise, right? So noise could be that there is a timestamp, right? There could be information about the author, right? There could be certain formats which makes no sense, right? It does not help you to understand whether you have let's say a real issue or not, right? So your logs always have 90 to 95% of the noise, and there are errors which are imprinted or hidden right in the logs, which are always let's say probably less than 5% of the overall log composition. So what is the solution here is applying the machine learning uh, to basically filter out the errors, right, and help the team to let's say utilize the power of AI and try to kind of make this a more automated, more AI-driven process. So the model basically automates the process of noise filtration and error triage in the logs. Now, I've just given a very high-level picture here. What is happening is that in the pre-MI, let's say the ML or AI environment, you have let's say the different kind of failure logs which is being generated. Then you have your own pipeline, and somebody was sitting here and analyzing the failure signatures and try to do a triaging. Now, with machine learning, what is happening is you deployed a complete machine learning framework which do all the activity, and you are just kind of infeeding your logs data into that model, and that model eventually tell you whether there is a noise and error, which eventually can be used for the automatic understanding of the triage flow, right? So essentially, it's an integration of the regular validation or the testing flow, but in feeding the logs into the machine learning framework, and that framework essentially use the techniques of NLP, which is natural language processing, and different classifications and the clustering techniques coming from the ML words, right, to understand what could be a potential error or the noise in these logs, right? So that's how the system work. Now, what exactly is the machine learning end-to-end deployment flow, right? So, since it's integration of the NLP and the machine learning, you can probably visualize there are 5 stages here. So one is called the data handling stage. The other one is called the feature engineering and the pre-processing stage. The third one is called the model training stage. Then the model selection and the integration and the deployment, right? So essentially what we are doing in data handling is we are talking about data collection and data balancing. In the feature engineering, we talk about some of the concepts of tokenization, vectorization, feature extraction, which is the important concepts in the world of NLP. Then we talk about model training, and here we have the concepts of stratification and model optimization. Then eventually, how do we select the metrics and the metrics integration. So when we talk about data collection and data balancing, what we are saying is that we have a logs data which is coming as a part of the test executions. It comprises of various elements, right? So your logs have different elements. For example, it has log file name, it has descriptor of the queries, it has classifications, it has a lot of different kind of signatures and many things, right? And what we do is we get these logs from our test execution cycle. And as I said, they are in the format of .log file or .error file or .csv file. But eventually what you need to do is you need to read this data, and then probably you need to write a script to convert this data into some readable format which can be infeeded for the further machine learning process, right? So obviously this comes as a part of the basic EDA techniques, right? What we call it as the extraction techniques and so on. So essentially, while you collect the data, it's also come up with, uh, let's say, a flavor of data balancing. So when I'm saying data balancing, what it means is that as I said, the logs are huge, and most of the time, 90 to 95% of the logs always have the noise, right? So when we execute the machine learning by parsing all the information, right, we need to understand that we would be having a problem of imbalanced data, right? So in machine learning world, what is imbalanced data is that if you have two classes, one of the classes highly skewed, right? So let's say if you have 100 sample point data for happy and unhappy customers, right? You will probably say 99% of or 95% of the data is happy, 5% is unhappy, right? So which means it's not a 50-50 data, right? It's not half of the class is happy customer, half of the class is unhappy customer. Now in this case, what it means is that we have different kind of signatures which are coming from the logs. 90 to 95% of those logs signatures or the prints are just the noise. So the errors are being probably even 5% or less than 5%. So it's a classic case of the imbalanced data, and that's why you need some kind of handling there. Now, the other parts, what you do is, as a part of the NLP is called the tokenization, vectorization, and feature extraction. What is tokenization is we try to break the data or the logs, right, into individual words or tokens. What is vectorization means is, in terms of NLP, vectorization means is that you convert your natural languages into some numerical data, because that's how machine learning understand. Machine learning does not understand the natural languages. Now, the bigger question is that why we are talking about natural languages, right? So the reason why we are talking about natural languages is that most of the time these logs are being generated as a natural languages, right? Which means they would be probably written in English or on specific language, and as the logs itself are being written in natural language, it becomes a problem to be solved using the natural language processing techniques, right? That's why we are talking about natural languages. And since natural language itself has some of the pre-processing techniques, for example, tokenization, vectorization, feature extraction, that's why it's very important to ensure that your logs, even though they are technical logs, but since they covers the natural language like English driven language, which is the complete logs is being written in a specific language, it has to go through a treatment of natural language processing techniques, right? Be it pre-processing or anything else. So as I mentioned, there are three main techniques. One is the tokenization technique, the other one is the vectorization technique, and the third one, which is also pretty important, is the feature extraction. So what we do is we try to extract features which are important. Now, obviously, sometimes the feature extraction is basic tokens is also a features, but you can sometimes you can have a well-defined features using some of the other feature generations and feature extraction technologies, which could be dimensionality reduction techniques or generating a new features based on maybe techniques like n-grams and so on, right? But essentially what we are saying is that once you have the data, you also need to go through some of the NLP techniques, which includes tokenization, vectorization, and the feature extractions.
Hey,
Now,
Tarun, quick
yeah,
question. What can
yeah.
you give me an example of some of the features that you would break down? Because that covers a lot of different things.
Yeah, so feature, when we say, see, in case of NLP, right, what happens is even if you consider the tokens, right, what you're extracting can be a feature, right? But let's assume someone will say, okay, the length of your signature text, the information what you're parsing, could be a differential factor to identify something as a noise versus error, right? So there could be a subject matter understanding or a domain understanding that, let's say, if you have a signature or a information coming from your logs, which is having, let's say, a length of 100 and more, right? It could be a potential indicator of the error. Whereas the length, if it is probably less, maybe 5 or smaller words, right? It could be an indication of noise. Now, this is probably coming from my subject matter understanding, but I'm converting this as one of the feature. So the feature here could be the length of the signature text. Now, the length of the signature text could be one of the feature for me, which I can analyze to understand whether this new feature which I have created, which is the length of my signature or my pass information, is it a differential factor or a feature to tell me whether a specific information can be categorized as an error versus noise? So Jane, I think the point here is that uh, there are various aspects of feature engineering, right? So you extract the feature by different techniques. So one is the simplest is tokens, right? So token itself is the feature. Then you can do something called the dimensionality reductions, right? So when you work in the NLP space, you generate a lot of features in different dimensions, right? So what you do is you also try to kind of uh, reduce the impact of dimensionalities, right? So you do some kind of dimensionality reduction. And then, of course, you generate certain features which are driven by the subject matter knowledge, right? For example, the length of the signature text, can that be a differential factor?
Okay,
Does
thank
this
you.
help?
Yeah, it does.
Yeah. So, of course, the other thing which is very important is stratification, right? So when we say stratification, it means that we make sure that we are using uh, the data as per its distribution, right? So what it means is that uh, in this context, your logs has huge amount of information, but that information uh, is highly skewed in terms of the noise versus the real errors, right? So we have to make sure that while we are doing the balancing, while we are doing the stratification, we retain the let's say the distribution of the noise and error while we do the modeling part, right? So any machine learning model if should make sure that we are handling the issues of balancing, specifically when we're talking about the classifications, right? So we should handle the problem of balancing stratifications and make sure that while modeling, we should not be treating the noise and the error as the same distribution, and make sure that the distribution is being retained as a model. Otherwise, this kind of models fails when they get into a production stage, right? So that's why stratification is important technique. Then there are some of the other important techniques. What we need to consider is something called the cross-validation techniques, right? So cross-validation techniques are a very good machine learning technique which help us to train the models in a iterative and incremental way, and it basically helps us to create a more robust models by let's say managing the biasness and the other variance factors into the system. And then eventually most of the models you use in the machine learning ensemble world as well as in the deep learning world, right, they always have something called the hyperparameters, and I'll probably explain that once we move forward. But generally what happens is if you play around with these hyperparameters, it will probably help you to get a more robust model, right? So it's very essential to understand that when we get into a machine learning problem, we make sure that all the basics of machine learning or deep learning are being taken care to get a much more robust models. Then, of course, if you try to let's say implement some of the machine learning classification like random forest, gradient boosting, and so on, right? Or if you even if you go to the deep learning classification like let's say CNN or let's say RNN and LSTM and so on, essentially what you are doing is you can use ensemble classification model, you can use basic machine learning models like logistic regressions and multinomial logistic regressions and so on, but you need to select your bucket, right? You need to make sure that you have a bucket of different models, because it's very essential to experiment your data with different models in this stage. Sometimes, right, ensemble can be more helpful than deep learning. Sometimes even a basic, I would say, a traditional machine learning models can be helpful, right? So you need to have your basket, which should have different kind of models coming from different worlds, and you try to understand which models fits into your data. But how would you understand is you need to identify certain performance matrices. So those performance matrices could be accuracy, it could be precision, it could be recall, it could be F1 score or whatever. But essentially what we are saying is how are you going to select which model is going to work best for you? For that, you have to ensure that you have the right set of performance matrices, right? So some of them I have listed here. Then eventually, once you develop the model, you need to make sure that your trained model should be uh, should be available in the binary format, right? Because eventually, what you want to do is once you have trained the model, that model has to be deployed in the production environment, so that the person uh, who is supposed to consume this model, right? They are not supposed to rerun these models and retrain this model, right? So those aspect has to be taken care. So once you have the model which is selected or a best model for you, what you need to do is you have to make sure that you convert that model into a usable format, right? You develop certain APIs, and then you integrate it into the flow, right? Which means that once you generate the log, right, you just need to parse the log, put it into this model files, right, and eventually it will going to predict what is the error prints, right, in your logs, right. So that's how generally the flow works. Now, let me just go into a bit more of details here. So let's assume that this is a kind of log, right? So this is just a one format. So if you see there are too many things, right, which is being listed here. So for example, there is a test number, there is a seed number, right? And sometimes, and these formats keep on changing, right? There's like thousands of formats, there are thousands of file tabs, right? So it becomes a complicated story. But essentially, what we're saying is all these prints has to be analyzed and figure it out whether they are noise or a potential error, right? So, for example, test number could be a noise, right? It does not make much difference, or it does not help me to differentiate it as an error, right? So things like test number or seed number could be a potential, let's say, a noise. There could be some statements which could be an error. Now, generally, when we try to analyze these kind of data, you will probably see that this data, these kind of data coming from the logs are always highly skewed, which means 90% of the data is always info, whereas maybe 5 to 10% of the data is error, right? That's why we were saying that this is a problem of imbalanced data, right? And it has to be handled while we do the modeling and so on, right? So this basically comes under a process which is called the data extraction and the EDA process. But the whole point is you need to make sure that you have the logs. Those logs is being converted, or let's say these fine prints has to be eventually passed, and it has to be infiltrated into your machine learning ops, right, or the machine learning flows. Now, one question which is very important to understand, this problem can be solved in two different ways. Okay. The one problem is that we can probably try to do some kind of ad hoc kind of unsupervised learning. But here, what we have done is we try to create this as a problem of classification or a supervised learning, where we have some engineers, right, who have been tasked to do some kind of a classification of these prints to train the model, right? So this was kind of done in the past also as a manual process. So it becomes easy for us to use that manual efforts which has been put for a year or two to feed that data into the model, right? So it become a classification problem because we have the logs which were manually categorized, or the prints which were manually categorized as the signatures versus let's say the noise versus the error, right? So that's where, if you don't have this information, obviously, you need to kind of do some kind of classification upfront using some manual effort, so that you can, let's say, save a lot of manual efforts in future by deploying the machine learning. But any classification problems comes up with some predefined labels, right? So in this case, luckily, we have those years of manual efforts which have already classified the signatures. So we could utilize that information to solve this as a classification problem, right, with pre-labeled data. Now, of course, when you work with an NLP, right, it comes with different kind of routines. So I've just listed some of the very basic routines, right, what you need to follow when you solve an NLP problem, right? So you will have a lot of garbage in your data, which does not help you to basically attain your goals, right? So what is happening here is that when you solve any NLP problem, you do a lot of cleanup. For example, you remove stop words, you try to reduce the features by doing lematizations, right? You remove a lot of noise, for example, date, timestamps, test cycle, seed cycle, and many other things. Sometimes you use regex operations to have certain patterns which makes probably no sense, and you try to remove that, right? And you tokenize the word. So generally what I've listed here is some of the low-hanging cleaning techniques or the pre-processing techniques, what we call in the word of NLP. So what we are trying to do is we are trying to do some cleanup of the logs, right? So that all the noise are being filtered before we get into a modeling stage. Why we are doing this is because we are trying to get the most important features which can eventually be fed into the models, and try to reduce the noise by removing some of the, let's say, the pre-classified noise, right? For example, stop word is a noise, right? Lemmatization is basically helps you to remove. Date and timestamp is a noise. There's no point in creating dates and different timestamps as a feature. There's no point in creating test cycle as a feature, right? So what we are doing is we are just removing this noise using a pre-processing routines, right? Which is a normal process for any NLP problem. I think someone was asking a question.
Oh, I was just going to ask you what lematize meant.
Lematize. Okay, that's a good question. Let me see if I can. Uh, okay, I need to remove this pointer, I guess. Let see what happens is, let's say in NLP, right? Let's say you have a word which is, let's say it is says words, okay, and probably it is says wording, right? So what happen is that uh, let's say you have two words. Now when you are working on the NLP problem, you have this as one feature and this as one feature, okay. Now what is happening is, uh, as a very basic or a golden rule for any machine learning is, the lesser and the most effective features, if you feed into the model, the more effectiveness you get out of it, because you're making it less complex and you're just infeeding the meaningful features, right? Now, if I don't do a lemmatizing here, okay, what is happening is it will treat wording and words, okay, as two different features. So, which means we are knowingly or unknowingly, we are infeeding too many features which basically are correlated to each other, and they are bringing the complexity without adding too much of value into the machine learning models, right? So when we do the lemmatizing, what it means is it breaks down these two words into its root word, right? So what it will do is it will just create these two as another feature which is called the word, okay. So what we are doing is we are reducing these kind of problem or these kind of feature into a single feature which is called a word. So it basically comes to a previous question of the feature extraction and feature normalization and feature engineering. So here also, if you see at a very high level, you're just trying to converting, let's say, different words which have a same, I would say, same root to have a single feature, right? So this is what lemmatizing is. It basically convert your different words into its root word. That's the simplest way of putting it.
Okay, that makes sense. Thanks.
Yeah. So as I said, pre-processing is pretty much helpful to reduce the noise features from the input data, and this is being done for any NLP problem, right? Forget about the problem what we are trying to solve, but if you're trying to solve any NLP problem, make sure that you are removing these noises so that you have a much more cleaner data to infeed. Now, again, as a part of the other techniques, we have something called the vectorization. Now, what is vectorization is, uh, see, any machine learning model, it does not understand the natural language. So if I infeed my logs directly into a machine learning model, it will not understand anything because they are in the natural languages, right? Now, these natural languages, as I mentioned, it could be English, it could be any other language, but let's assume that we have our data in the English language. which is not understood by the machine learning model, because machine learning model understand let's say the mathematical stuffs, right? So vectorization technique is basically helpful to convert your natural languages, okay, into a numbers. Now there are various techniques. It could be as simple as TF-IDF. It could be a single step neural techniques like word2vec, doc2vec, fast text, and many other. It could be other simple techniques like count factorizer, or it can even be transformer based, for example, bird embedding and so on, right? So essentially, all of them, what they are doing is they are converting your, let's say, a feature, which is an English language, let's say, word, okay, into some number. Okay, so let's say that number is 1.5. Okay, now this 1.5 is coming out of any of these techniques which is being applied. So all of these techniques have their own pros and cons, but just to give a context, whenever you're done with the cleaning of the NLP, what you do is you convert your, uh, let's say, the textual data into a numerical data, so that that numerical data can be infeeded into a machine learning model. So that's why vectorization comes as an important technique.
Okay. Hey,
Now,
Tarun,
yeah.
sorry to break in, but I think we have 5 more minutes. So,
Correct. So I'll try to finish it fast in the next
okay,
5 minutes. Yeah.
thank you.
So what is happening is then, of course, what you do is you try to apply different machine learning models. Once you have a vectorized data, what you do is you try to put it into traditional machine learning models, which could be support vector or logistic regression or naive Bayes. You can use different kind of ensemble, for example, random forest, or it could be gradient boosting, right? Or if you want, you can even use another techniques like deep learning, where you can use, let's say, CNN, you can use LSTM, you can use uh, GRU, right? Simple neural net, whatever you want to do. But essentially, what you're doing is you are feeding your data into this model, and eventually, what you do is you try to analyze these data on various matrices like precision, recall, F1 score, and you try to understand what is the best model you should fit in, right? So here what we did is we tried to find a model which is having the high precision and recall for the error prediction, right? So we are not worried that if by mistake we are categorizing some let's say noise as error. We are more worried that if there is any error which is being wrongly categorized as a noise, because that is more fatal to us, right? So while we choose the model, we have to make sure that we are using these matrices and make a conscious decision that which is the right metric. So that's what we did here, right? So we figured it out. Okay, the support vector machine and RFC, or which is called the random forest, they were working pretty good. But when it comes to the random forest, it was giving the false negative rate of error is almost 0.5, which means that it is not detecting any noise, uh, right? Or I would say any error as a noise, right? So that's why you can select the model based on the performance matrices. Now, obviously, what is being done here is you actually integrated the trained model. Let's say in this case, I put random forest with the validation flow. So this is the original flow. This is the machine learning flow. All the models which is being trained. So now you have the past data. This data feed it into the machine learning model. All these activities happened, right? And then it eventually tell you, okay, this signature is error, or this signature is a noise. If it is a error, obviously you try it to a bug, right? That's why the complete end-to-end flow comes into a picture. So all the modeling has been converted into an integration flow. Now, what are the key learnings? One is the stakeholder collaboration, right? So this is very important. The second is that we need to perform a lot of good pre-processing, and model generation is always an incremental and iterative process. You cannot have a one good model and one pre-processed data once upon it, only at once go. You have to do it as an incremental process. And we should not just look into the accuracy metric. We should look at the very other metrics like precision and recall to make sure that we are not losing on the model just by looking into one metric, right? So that's why looking into the metrics is very important. Uh, and the important thing is that how you make it as an integration success. You have to make sure that you integrate your model binaries with the engineering flow. so that they can leverage the model efficacy. You should enhance the accuracy by making sure that you are doing a lot of good pre-processing and involving the right stakeholders. You can gain a lot of efficiency by applying advanced NLP techniques and advanced deep learning techniques, and make sure that you are categorizing the failure signature with utmost precision. And then we want to make sure that we are reducing the manual intervention. So in this case, what happened is now you don't need any manual intervention because your machine learning or the AI model themselves are diagnosing the errors and predicting the errors and helping you with the triaging process. So you should have a seamless integration and you should reduce the manual intervention. And essentially what you're doing is you are basically giving a foundation that how various aspects of software operations can use machine learning and AI to enhance their productivity, to enhance their efficiency and effectively, right? As I said, it's very important that we apply AI and ML techniques in our operational domains to make sure that we leverage all the benefits of AI and ML. With this, I'll take a pause, and I believe I'm already on the top of the hour. Thank you. Thank you, everyone.